Alright, let's look at some second substitution examples, how we might go about doing them. Alright, so what we're looking at here is a situation where we have an OMe connected to the ring. And when we're looking at these, what we really want to do is focus on the atom directly attached to the aromatic ring. Find out whether it's going to be delta minus or delta plus, because that will tell us whether it's going to be activating or deactivating. So just focusing in on our O methyl group, which is really OCH3. What that is a single bonded oxygen, which means it's got two lone pairs, so we know this is going to be a delta minus. If that's a delta minus, then that means that we are indeed talking about an activating type situation, so electrons are going to be pushed into the ring. So that's the first thing we do, figure out whether it's delta minus or delta plus, which tells us whether it's activating or deactivating. The next thing we do is we look at the reagents above the arrow and we try and figure out what the electrophile is going to be. If it's HNO3 and H2SO4, the electrophile is going to be NO2 plus. Now we know this because when we add the H plus to the HNO3 and we lose water, what we're going to be left with then would be NO2 plus. It's almost like you can see the NO2 plus hiding in there anyway. Alright, so we know that we're going to be activating, so we're going to have we're going to be going ortho and para to the group that's already attached to the aromatic ring. Alright, so that's one product, and the other product will be the para product. Now the NO2 won't just add twice to the same compound. It will always form two separate distinct products. The reason for that is because as soon as we add the NO2 group to the aromatic ring, it actually begins sucking electrons out of the ring, which makes it less attractive to electrophiles. So once we have the NO2 on there, another NO2 going on is just not very likely. So we're going to get a mixture of ortho and para products. Now it's worth saying that the mixture is probably going to be about 66% of this one and 33% of this one. Now the reason for that is just sheer numbers, because we have two possibilities for ortho groups and only one possibility for para, so we'd expect a 2-to-1 ratio for each of these products. Alright, in the next one, again we focus on the group, and we're really going to focus on the atom directly attached to the aromatic ring, which is this C right here. And we know that that's going to be delta minus, which means that the C connected to it is going to be delta plus. Now if that's a delta plus, what that means is that electrons will be sucked out of the ring. So we know this is going to be a deactivating situation. Right, the next thing we need to do is figure out what reagents we're using and what kind of electrophile we're going to get. And the electrophile we're going to get out of this will be Cl+. Now there's a little trick you can use. What you can do is separate out the Cl and the Cl and the FeCl3. And we know what's going to happen is that the FeCl3 is going to grab one of those Cl's, and what's left over will have a positive charge, and that will have a negative charge. So that's a good way of being able to tell what our electrophile is going to be. So we know that Cl plus is going to be our electrophile here. And as we said, this is going to be a deactivating situation, so we're looking at meta, and just one meta product is all we're going to get. Remember that both of these meta positions are equivalent, and putting it on either one is going to give you the same compound. Alright, so there you go. So that's for that one. Now in this case we've got an N connected to two methyl groups, and that means that we're going to have a lone pair on the nitrogen, which means we're going to have a delta minus, and a delta minus means that we're going to be pushing electron density into the ring. That means that this is going to be a activating or an activating type situation, so we're going to be looking at ortho and para products. Again, we need to figure out what the electrophile is going to be, and we're going to use the same strategy as we used in the one above. And what we can do is draw it out completely, showing the CCl bond, and recognize that the Cl will join on to the AlCl3. That'll be negative, and whatever's left over is going to be positive. And the join will always be to the atom that was attached to the Cl, so that's where the ring will join as well. So we'll see that. Alright, so again the electrophile is this. And the join to the ring will always be through the positively charged carbon atom, which was the one connected to the chlorine. Okay, so the product here, one of them, will be this. And this. Alright, so we're getting ortho and para products from this activating group. Alright, the next one. We've got a COOCH3. I'm going to have to draw that out. And if I draw it out completely, I know that it's going to look like this. It's going to be C double bond O O CH3. Now it's the only way I'll be able to figure out if this is activating or deactivating is to actually physically draw it out. So this C is obviously this C right here. So what we can do is we can say, well, that's going to be delta minus, which means that this is going to be delta plus, and since this is delta plus, we know it's going to be deactivating, so electrons are going to be pulled out of the ring. And if that's the case, then we're looking at a meta product. Now we already know what the electrophile is. We know it's going to be NO2 plus. We figured that out from the first problem we did. So I'm just going to use that information again. NO2 plus. And since we're looking at a deactivating group, we are going to get just a meta product right here. Alright, let's look at the next one. We've got C double bond O, we've got COOH, and if we draw that out, it's going to look like C double bond O OH. Now when you're drawing these out, just realize that the way you draw them is to make it so that the C has 4 bonds and that the oxygen, each oxygen ends up having 2 bonds. And the only way that we can express this and have it make sense is to have the C double bonded to the O. There's no way that we can do something like this. It just does not work out because now you have short bonds on the carbon, so we know that that just does not make sense. The only way we can make it make sense is to double bond the C to the O and bond the C to the OH. And that is the accepted way of writing that. Alright, so if that's the case, then what we're looking at is a delta minus on the O and a delta plus on the C, and that's the bond directly connected to the ring, so we know that this is going to end up being deactivating, so electrons will be pulled out of the ring. And with the nature of the electrophile, need to figure that out now as well. And what we'll do is we'll do what we did before. We'll draw this out a bit, showing the bond from the Cl. Again, we'll circle the Cl with the AlCl3. That'll be negative, and whatever else will be positive. So our electrophile will be CH3, CH2 plus, with the positive charge being on the C. Now this one can't rearrange, because if it did rearrange it would just form another primary carbocation, so it's pretty much stuck the way it is. Remember, the rule for rearrangements is that if it can rearrange it will. In this case it can't, so it won't. Alright, so there's our electrophile, and now we can go ahead and add it to the ring, and since this is a deactivating group, then we're looking at a meta product. And again, the join to the ring is through the positive, where the positive charge was, which is on that carbon atom. Alright, this next one's a little bit tricky. What we've got to do here is look at, again, what's directly connected to the ring. And the atom directly connected to the ring is not the C double bond O. So you might see the C double bond O there and think, oh yeah, that's going to be deactivating. But since the C double bond O is not directly attached to the ring, it's not going to have an effect on the activating or deactivating effect of this group. What is going to have an effect is this atom here, the one that's directly attached to the aromatic ring. And since this is a single bonded oxygen with lone pairs on it, then it's going to be delta minus, which means this is going to be activating. So this is going to be an activating group. It's going to be pushing electrons into the ring, and that's going to give us a ortho and para product. Alright, let's look at the electrophile, and we've got Br2 and FeBr3. So again, we draw this out. And we know that that portion is going to be negative and whatever else is going to be positive. So the electrophile here is going to be Br plus. And now we can go ahead and draw our products, which are going to be ortho and para products. So we'll have a Br here, and we will put a Br down at the bottom here as well. So ortho and para to that group. So again, just reiterating, we're only interested in the atom directly attached to the aromatic ring. That's going to tell us whether it's activating or deactivating. Don't worry about the rest of the group. On this one, we've got an alkyl group, and alkyl groups tend to be activating due to hyperconjugation. So what happens is that if you've got this kind of thing, we've got a CH2, CH3 as well, and the ring's down here, and what can happen is the CH bonds can donate electron density to the ring. It's not very strong, but it's certainly still an activating effect. So we know that this is going to be activating. So again, our products will be ortho and para products. Ortho and para. And again, we're using the Cl plus as being the electrophile because we found this over here in this part of the problem. Okay, let's look at the next one. We know again that the electrophile is going to be NO2 plus, so I don't have to go find that. And we do have to look at the NHCOCH3. Again, I have to draw this out. If I draw it out, here's what it looks like. I have an NH, and then this will be connected to a C double bond O, and this will be connected to a CH3. The ring will be down here, and again, what we're interested in is the nature of this particular nitrogen, which does have a lone pair on it. And since it has a lone pair, it's going to be delta minus, which means that it's going to donate electrons into the ring, and it's going to be activating. So again, we don't worry about the C double bond O because it's not the group that's connected to the aromatic ring. Alright, so let's look at the products. Products are the para products. Sorry, ortho and para products. Ortho, and para. I'm going to run out of room here. So NHCOCH3 and NO2 down here. So we'll have our ortho and para products for that particular one as well. Alright, so in summary, here's what we're doing. We're always looking at the nature of the atom directly attached to the aromatic ring. If it's double bonded to an electronegative atom, it will usually have a delta plus on it. If it is just an electronegative atom that's single bonded, then it's going to tend to be a delta minus. So that's a good little rule of thumb for you to use. Always be aware of how to write these shortened structures out to make sure you see any hidden C double bond O's and such in those kinds of structures.